Welcome to the NOAA Science Seminar, Deepwater AUV and ROV Surveys for World War II Underwater Cultural Heritage in the Saipan Channel. This presentation will explore the historical context of the Commonwealth of the Northern Mariana Islands, or CNMI, in World War II, and discuss the project methodology and results of using autonomous underwater vehicles, or AUVs, and a remotely operated vehicle, ROV, to locate and document multiple U.S. World War II B-29 aircraft lost in this area. This project was supported via the NOAA Ocean Exploration Fiscal Year 2020 funding opportunity. This science seminar series is co-hosted by the NOAA Ocean Exploration and the NOAA Library. My name is Garrett O'Donnell. I am a 2025 Guam Sea Grant Canals Fellow working at NOAA Ocean Exploration in the Science and Technology and Outreach and Education divisions. I'm excited to introduce you to our science seminar speaker today, Dr. Andrew Pietruszka. Dr. Pietruszka is an underwater archaeologist at the Scripps Institute of Oceanography, University of California at San Diego, specializing in the search, documentation, and recovery of U.S. service members missing in action due to our nation's past conflicts. He received an MA in underwater archaeology and maritime studies from East Carolina University and a PhD in anthropology from Syracuse University. In 2011, Dr. Pietruszka joined the Defense POW MIA Accounting Agency, DPAA, as a forensic archaeologist overseeing underwater recovery operations. In 2015, he served as the interim director of DPAA's laboratory at Air Force Base in Omaha, Nebraska. In 2016, he left public service for an academic research position at the University of Delaware. Since 2016, he has served as the lead archaeologist for Project Recover, a collaborative effort to enlist 21st century science and technology to find and repatriate Americans missing in action. So without further ado, I wanted to thank you for your time today, Dr. Pietruszka, and for sharing your wonderful research with us today. And with that, I'll hand the floor over to you now.
Thank you, Garrett, for that very nice introduction. And welcome everybody online. I'm excited to share this presentation with you. I'm going to go ahead and turn my camera off. So today I'm going to talk about an exploratory ocean survey where we use autonomous underwater vehicles and a remotely operated vehicle, or an ROV, to locate and document multiple U.S. World War II B-29 aircraft that crashed offshore Tinian and Saipan in the Commonwealth of the Northern Mariana Islands. This research was funded by the NOAA Office of Exploration and Research, so we're very grateful for that. And this was originally funded way back in 2020, but we had a big delay due to COVID and stuff. So we actually were delayed 2 years in executing. Before I sort of get into the actual sort of survey and the technologies that we use, I wanted to give you a very brief introduction to the history of the island. So the Japanese administered the Northern Mariana Islands since 1914 and captured Guam from the U.S. in the opening days of World War II. The CNMI served as an important waypoint for Japanese forces in the Pacific, providing pivotal reinforcements and communications. The U.S. knew the importance of these islands, and they embarked on Operation Forager, which was the U.S. offensive against the Mariana Islands. And there's really two sort of strategic ideas that back this. One is they wanted to break a key component of the Japanese line of defense. And two, they wanted to bring Japan within striking distance of the U.S. B-29 that had been developed. So air bases developed in the Marianas Islands would be able to allow for those attacks. So the strategic importance of these islands was critical, and it was so critical that the construction of an airbase suitable for B-29s began even before the end of the ground fighting took place on these islands. 3 air bases were constructed in the Northern Marianas, 2 on Tinian and 1 on Saipan. Saipan did not prove to be suitable as originally thought, so more runway was added, and the runway, which would be known as North Field on Tinian, was expanded even more pretty rapidly. When finished in November of 1944, North Field in Tinian was the largest airbase in the world. East Base was large enough to accommodate a bomb wing consisting of 4 bomb groups, or a total of 180 B-29s per airfield. And these bases became the launch point for the release for the relentless B-29 sorties against Japan in the world's final year. Some interesting facts about the B-29 aircraft itself. It was one of the most technologically advanced airplanes of World War II. Its design and development was rooted in the Army Air Corps' acceptance of a strategic air power doctrine that required a very long-range bomber capable of providing high-altitude precision bombing of strategic targets. It was one of the largest aircraft of World War II. It was twice as heavy as the B-17. It was manned by a crew of 11 individuals, and it had a length of 30 meters and a wingspan of 43 meters. So some of the innovations, the B-29 was an extremely innovative aircraft for its time. Some of the innovations that were first developed solely for the B-29 were cabin pressurization, a remote-controlled analog computer gunnery system, dual-wheeled tricycle landing gear, radar for navigation and targeting, and the incorporation of a new engine, the Wright R3350, which was the largest engine available at the time of its development. The B-29 program was the most expensive military program of the entire war. Most people think of the Manhattan Project. The B-29 development was actually $3 billion. This is dollars in the 1940s. $3 billion cost for design and production, where the Manhattan Project was only $1.9 billion. That just sort of shows how important this aircraft and these islands really were to the American strategy of going after the Japanese homeland. And then, of course, one of the reasons we study history so much is because, history repeats itself. And you may have seen in the news, but the United States military is currently right now redoing North Field on Tinian, and they're building it back up to make it an operational airbase as we continue sort of our strategic push in the Pacific. A little quick note on some of the previous archaeological research that was done in the area. The larger circle here, this area called which is Saipan Harbor. It's a shallow area harbor, and there's been a lot of work done by Jen McKinnon out of Flinders University during her PhD work, and now she's at East Carolina University, where they've been looking at World War II craft from the landing during the land campaign, as well as aircraft that are in that area. They've come up with a really cool maritime trail, and it's sort of, when we looked at it, it gave us an idea of the quality of preservation of World War II cultural heritage assets there. There was also a small survey here for a certain B-29 called the Jolton Josie. That was the first B-29 to land in the Northern Marianas. And so it sort of has that historical significance, and it crashed on takeoff. There was down in Tinian and Tinian Harbor, Project Recover, a group that I'm associated with, did some shallow water work. And then in 2016, NOAA, the ship, the Okeanos Explorer, did some research with some multi-beam in the area, did some survey, and was able to discover some targets, and ultimately discovered a portion of a B-29, which I'll talk a little bit more in a bit. The key here is that if you notice, all 3 out of the 4 are all in shallow water. So our research was sort of building on the NOAA research in terms of trying to expand deep water access and deep water archaeology. Some of the project goals, I'm just really going to focus on the first 2 during this talk, which was providing an inventory of submerged cultural sites in the area, particularly in the deep water area that we were looking, and then sort of research and development with looking at novel sort of technologies to both do survey as well as documentation. When we first began to look at this area, I think it would be disingenuous to not share that there was some previous research by a gentleman named Jeffrey Meyer. His charts, that one on the left with the circles, he was a historian with the United States Air Force 36th Wing. And he was looking into a lot of these losses, B-29 losses. And so we took that information as a starting point, and we began doing more additional historical research of our own. And we did come up with some differentiations between them. Most notably, some cases like there's one case, pilot's name is Preston, where the Macker map and the written description and the coordinates given by the rescue ship all point to different areas. And that's sometimes what we have to deal with when we're dealing with historical records. Sometimes there can be discrepancies. And so we have to sort of take those into fact. So we looked at a bunch of different records and we kind of came up with our projected survey areas, which are outlined there in red. So some of the equipment that we used, we'll first start with the research vessel. This is the research vessel Kilo Moana out of the University of Hawaii. The Kilo Moana is a 186-foot long, what we call a swath, a small waterplane area twin hull vessel. That is a fancy word for a catamaran. Owned by the U.S. Navy and operated by the University of Hawaii as part of the UNOLS fleet. It gave us a great platform for running our different instrumentation off of, but it also has its own instrumentation for doing oceanographic mapping and research. Most key to our research was its multi-beam systems, which provide a three-dimensional view or map of the seafloor. And you can see our colored one here. That was all new bathymetric data that was recorded during this endeavor. Next piece of equipment I want to talk about was our autonomous underwater vehicle, or AUV. Sometimes you might refer to them as a UUV. For this project, we used two Remus 600 AUVs. If you look at the top of your screen there, that's the yellow torpedo-looking thing. It's a 600-meter depth rated vehicle, so it can operate in depths up to 600 meters, or about 1,800 feet. It has an array of sensors that we can put on it. So we have side scan sonar, we have multi-beam sonar, and we had cameras that we can put onto it, as well as other oceanographic instrumentation. These are fairly big vehicles. You can see the picture of us working on the deck to launch it using the A-frame at the back of the ship. It takes several people to sort of work it with the crane for safety to get it in and out of the water. The way that these vehicles work is, because they're autonomous, is we pre-program them to run a predetermined survey pattern. What we typically use for our wide area surveys when we're trying just to locate anything on the seafloor in a wide area is a mow the lawn pattern, where we just kind of go back and forth in rows. So that's pre-programmed onto the vehicle. What we do is we place a series of deep water transponders. If you look at the middle sort of graphic there, those are the gray things floating up in the water column. And we place those into the water column onto the seafloor, and they're floating up. And we're able to use sort of acoustic methods to give us a very precise location of those floating sensors. And those sensors are anchored to the bottom so they don't move. So once we know those positions are established and they remain there. And we provide the vehicle with those positions. And then the vehicle sort of drives itself back and forth through this field, and it talks to those sensors acoustically as well. And basically it can use their positions to know its own position through triangulation or trilateration. One of the key pieces of sensor equipment that we use for the wide area survey is side scan sonar. So this is an acoustic burst out of the side of the vehicle, has sensors along the side. If you look at the very top, that's that black bar along the side of the vehicle. And these acoustic pulses, they shoot out from the side, they hit the seafloor, they reflect back, and the computer algorithm is measuring the time and distance, or the time that it takes for the sound waves to travel from the vehicle to the ground and back, and it's able to determine and provide a two-dimensional picture of the seafloor based on that. And so any objects that are sticking up from the seafloor will be shown in that two-dimensional. So just some examples on the bottom. To the left is a B-29 that we're going to talk about. That's the one discovered in 2016 and redocumented by our group. In the middle is just something to show you a little bit of scale. Those two airplanes are drawn to scale. So that's a B-29 and a little single-seater P-38 Lightning. To the right is an example of a side scan sonar image of a P-38 Lightning that we use as a test case here in La Jolla, just to show you sort of scale. And to the right is another small aircraft that we'll talk about. So how do we find or how do we analyze a side scan sonar? This video is actually how we review the data. Once we get it off the vehicle, it's coming in, we scroll through it, and we're looking for anomalies that stick out. In this case, we can see one here. This is from a different survey that ended up being the wreckage of a B-24 aircraft. The next piece of equipment that we used was an ROV. So we had the ROV Beagle, which is a custom-made ROV designed by Marine Applied Research and Explorations, 1,000 meters rated, and it basically had a whole bunch of camera arrays on it for us to use in this project for documentation. What did we accomplish? Well, over 12 days on station, we were able to cover 200 square kilometers of ship-based multi-beam, 46 kilometers of side-scan sonar, conducted 6 ROV dives, and collected over 9.5 terabytes of data, which is a whole lot of data. Some of the finds that we had. So the first find I'll talk about is we came across what we were able to identify as a TBM or TBF Avenger. If you remember from the beginning, my emphasis was on B-29s, and that's really what we looked for in the historical record. We did know, from reading about the U.S. invasion that they softened up the defenses by having a series of offensive maneuvers by aircraft carriers that supplied aircraft to the area. So we knew there was a possibility of finding smaller fighters and fighter bombers, such as the TBM, as well as Japanese aircraft, but we didn't know the exact ones that we'd be looking for. So it was kind of nice. It was a brand new find in the area that we're still working on trying to narrow down exactly its identification, but we are confident in the type of aircraft that it is. We also came across what we are still referring to, unfortunately, as an unidentified aircraft. We're pretty sure this is World War II vintage. It's only about 350 meters away from the TBM site, which is interesting, although in review of, I think I've reviewed over 250 TBM cases in the area, none of which had a collision with another aircraft. So it could just be that, they just happen to fall very close to each other at different times. But maybe we'll still find that in the historical record. What we do know about the site is that the aircraft had 2 engines. They're twin radial engines, likely only a 3-way prop from what we can see. The square oil cooler, which is in the upper left of the screen there, is very unique. Most oil coolers, especially from U.S. version World War II small aircraft, are circular or oval. And a landing gear mechanism. But unfortunately, we continue to look and have not been able to identify it. My hunch is that it's a Japanese aircraft. I've reached out to some experts and hoping that they can sort of help us continue researching that one. The next is the B-29. So this was initially found in 2016 during a multi-beam survey by NOAA. During that survey, there was 4 targets, which they nicknamed Romeo, Juliet, Oscar, and Wild. All those were at a depth between 330 and 380 meters. That same year, after they had the multi-beam data, analyzed it, saw these targets, they were able to come back a few months later, and they conducted a single 7-hour ROV dive on 2 of those targets, Romeo and Juliet. And those dives were actually pretty cool. They were a live stream done by NOAA, with a large shore-based scientific team that participated via telepresence. I was actually very fortunate to be one of the archaeologists invited to take place and be part of that scientific team. And so it was a really fascinating find. And again, sort of when we were gearing up to go do our project, we thought that the discovery of this site in 2016 was very promising for what we might find in the area as well. Some key components from this site. So that main area, that's an inverted portion of the wing, complete with both a landing gear, and 3 of the 4 engines are still attached. There's also attached fuselage debris trailing that with parachutes intertangled within it. Found engine 3 is disarticulated from that, but it's lying close by in the debris field. Also discovered a portion of the forward crew compartment with forward gunner, turret, flight engineer panels. Also the pilot or co-pilot seat with a flak jacket and the horizontal stabilizer. The middle top image there, so the top left, that's the NOAA ROV down on the site in 2016. The middle image is a 3D model that was created from the ROV footage by Dr. Megan Lickler-Mondun. And to the right is our image captured in 2019, also a three-dimensional photogrammetric model. In 2016, they weren't able to ID the aircraft other than being able to tell that it was a B-29. In the general map there in the middle, the blue one represents the find from 2016. As you can see, there's multiple other B-29s, 4 more that it could be. So we're pretty confident it's one of those 4, but we can't narrow it down at this point. So when we went in during our survey, our general focus was see if we could capture any more information that might help us ID the aircraft, find new portions of the aircraft, collect comparative data about site formation processes, and see if we could delineate crew positions and search for associated remains. We wanted to capture deliberate ROV video so we could make 3D reconstructions and capture AUV images so we can make a full 2-dimensional site plan. We wanted to interrogate the additional targets, Oscar and Wild, which we did, and they ended up not being anything associated with aircraft. They were just natural rocks. Some of the new observations that we were able to capture during our work is we identified 6 to 7 parachutes on site. That's a strong indicator that the air crew's remains still might be associated with this site. We ID'd components of the radio operator station, the navigator station, and we were able to document the forward section. Unfortunately, we were not able to capture any additional information, and the plane still remains without an ID. Now I want to move a little bit away from our finds and sort of into the technology side of things, some of the different technologies and techniques. We already talked about the survey techniques, but these are more sort of on the documentation side of our project. So the first was ROV-based photogrammetry. I'm not going to spend a ton of time because this is something that's been done for quite a while. It's not extremely novel. But we did use it during our expedition, and we wanted to sort of compare and contrast it to what we could do with the AUV, which I'll touch on at the end of my talk. So this is a TBM Avenger from that TBM site. This is the engine of it. And the way that we work is we put the ROV down from the ship. This site is about probably 340, 350 meters deep. So the ship holds station over top of it. The ROV is dangling down on a giant tether that's connected to the ship. And then we can run the cameras that we can see real time. So what we start is by taking video of the site. And typically when we're trying to do photogrammetry work, we work sort of in a spiral where we go around and we're trying to capture as much of the individual object that we want to make a model of. We usually start low and we slowly kind of come up. And if we're going in a clockwise, usually once we get to the top, then we'll kind of reverse course and go in a counterclockwise on the way down until we capture the whole object, usually from 2 different perspectives. From that, we're able to take that video and using different software, we strip out individual images. So this is a series of 5 sequential images taken from that video that you just saw. One of the things to point out is you can see how little is changing between all of these images, and that's really important when we try to make these 3-dimensional models. Is we want a lot of overlap between these images. So when the software is trying to align and make this photo mosaic, it has a lot of common points between each image. We're using a software program called Agisoft Metashape Pro. to make our two-dimensional orthomosaics as well as our three-dimensional models. So this one had, from that video, we were able to extract 826 images. And we had 508 of those aligned when we did the reconstruction. So we got about 61%, which is actually fairly low, yet we still got a pretty good model. And unfortunately, this is on PowerPoint, so I can't manipulate it. But if we were using a different software, you'd be able to rotate this all around and move this in three-dimensional space and see the back of it, see the front of it, top side, whatever you wanted to do. So it's a really good tool for archaeologists studying a site, as well as a really good tool for helping bring sites that are in very remote places, whether it's deep water or out in the middle of the Pacific, able to bring those to audiences who can't make it to the sites, or and that helps us tell the story of history. This is another one that we made. So again, this is a three-dimensional model. We're seeing it in 2 dimensions right now. This is of the B-29 front top turret and the forward fuselage. This one had 2,450 images, 2,383 of those lines. So we had about 97.2%. And hopefully it's showing, I think the amount of detail in this one is quite a bit more than the last one. And then the last one I'll show you is a B-29 engine from that same site. This one was actually only compiled of 56 images, where we got all 56 to align, so 100% alignment, and we got a pretty good model out of that. What I want to spend a little bit more time on is our AUV payload and how we do imaging with that, because this is a fairly new technology that we've been working with this company, Voyis, in the development and testing. So the Voyis Recon AUV payload is a modular 4K optical imager. It's easily integrated. Sort of on the left, you can sort of see the component that gets slid onto the vehicle in its nose section, and that's the camera that faces down, and then a strobe light for illumination. It's a 12 millimeter lens. It's got a field of view of 60 degrees in the horizontal, 46 in the vertical. It's got about a 7-meter range. Frame rate is variable. Depth limitation of 1,000 meters. And a strobe that's capable of 500,000 lumens. So it really can illuminate, which is good when you're working at depth where you might have little to no light. You need that illumination. One of the neat things that utilizes the AUV's existing navigational data to deliver georeference images. So not only is it taking images, it knows exactly where those images are in space, because the AUV vehicle knows exactly where it is in space. Once you take those images and you bring the vehicle back on board and you offload them, then you use some proprietary software called VULS Data Module for data processing. And the way that they come off, you can see sort of the black square. That's what the images look like before you run them through the processing model. And then once you do, it provides it basically assigns the navigational data to each image. It corrects the image for water distortion and any uneven illumination, and it does machine learning for color correction for true color based on the whole batch of images you put in. And so you can see sort of the resolution and the clarity you get. The top is black squares, how it comes in. The bottom with the ray there, that's an example of a single image taken with this vehicle and the camera system. Again, we're using a Agisoft Metashape then to take all of those images and do our photogrammetry processing with them. And just to give you an example, so that's again just a series of still images on the top there. We take a whole bunch of those, we put them together, and the bottom composite is a two-dimensional orthomosaic, but we could also do a 3D model of an engine of an SBD. And just to show you sort of like the comparison of what this data looks like for us, to the left is a side scan sonar image of that same engine. So clearly the amount of detail available to researchers with the optical versus the acoustic is quite significant. Some of the AUV photogrammetry projects that we did during the Tinian and Saipan project. So we did the AUV photogrammetry of the B-29 fuselage. We talked a lot about the B-29 already. So what we were doing is we had an algorithm where we could only capture images within a 50-meter radius. So on the right is the red represents the planned survey pattern that we programmed into the AUV. The white is the actual vehicle path. Those big loops are the vehicle has to go out of its survey area, make a big wide turn called a Williamson to come back in and get back on track to the next line it's supposed to run. And because of that, you will capture a whole bunch of images that you don't need outside if you had the camera running continuously. So we restricted to a 50-meter radius for the point of the known point of the aircraft. So this circular area represents 7,854 square meters. It's comprised of 13,720 images, and it took about 3 hours vehicle runtime to capture that data. Here's another example. This is the TBM Avenger site that we discussed. We ran the same pattern, so it's the same area, 7,854, and the same number of images, 13,720 images. Also took about 3 hours to run this. On the left, you can see we actually got a little bit lucky. Our coordinate was a little bit off, but we still captured it in our 50-meter square. And on the right, just showing you an example of how you can zoom in. Some of these images are extremely, when we make these mosaics, there can be sort of, somewhere in 2 terabyte land, sometimes in size, depending on how many images and stuff they're comprised of. But that also gives us very, very fine resolution that we can zoom in on. This is an example of that resolution I'm talking about. So this is from a different time that we were testing out equipment. This is a modern boat, also probably about 500 meters deep, running the same exact AUV and camera system. And you can see the level of detail, right? Like not only can you notice the toilet that's in the boat and the bucket, but we can zoom in further and see the actual bolt pattern of the toilet and see the braided strands of the rope down here. And why this is important is not just, it's incredibly cool from sort of a nerdy tech standpoint, but it's also very helpful when we're analyzing wrecks. So on the right is sort of an example of a site that we were on. This is a B-52, so you could think Vietnam era, that we were trying to determine what type of aircraft we were on. There's very little wreckage sitting proud of the seafloor, and we were able to find this dial with these various knobs, which we were able to go back and look at catalogs and stuff and match them up perfectly to the pressure demand oxygen regulator that was only found on B-52 aircraft. So being able to see that fine level of detail can help researchers determine exactly what type of aircraft or other information, if they're not working on aircraft, on different types of sites that they might be interested in. We can also do something called digital elevation mapping, where we can take the images and we can take the information from the vehicle, which gives us its altitude, and we can then use that to determine elevation models. So color coded for things that are higher, right, are in the red, things that are lower, and we can look for things like depression scouring, and sometimes it can actually make it easier to see certain portions of the aircraft. An example of this, again, this comes from a different case, but we were working a B-17 in Sweden where the case is completely overgrown with algae and seaweed. And when we ran our traditional AUV-based survey with the camera and we stitched it together and made this model, it did a good job of capturing the seafloor, but it's very difficult to discern individual components of that site. When we switched it over to digital elevation model, you can kind of think of this almost like LiDAR kind of works. It's completely different technology, but like LiDAR lets you see through the trees and they detect all kinds of cool temples and stuff like that in South American stuff. This is allowing us to see through the seaweed and algae, and we're able to detect the various components of the aircraft. One of the other things that we were trying to do, albeit unsuccessful, but that is science, right? We learn through trial and error, is we wanted to sort of explore what was the largest area of the seafloor that we could continuously image in like a single mission with the AUV. So we set out to do a fairly large area. We wanted to focus on the B-29 because it had a large debris field, right? So it had multiple components that were spread out over distance. And this is where, rather than looking at each individual component, seeing how these pieces are distributed across the seafloor and how they relate to each other, and looking for different objects within that debris field could be extremely beneficial. So we tried to do basically a 300 by 100 meter box, that's the red, over the B-29 site. And then we had another 50 meter box over another site. We combined them all together for about 37,000 square meters. Unfortunately, we ran into some issues with, we had a very strong current there, navigational issue with the vehicle. It was an old version of the software. Basically, a whole bunch of things kind of all came together to make it a difficult mission. As you can see from our mosaic, it didn't work very well. But we did learn a lot from our mistakes, and we've continued to work on this problem. And we've made a whole bunch of strides, and we've learned a whole bunch of other problems that we face when we're trying to do this. So when we were originally approaching it, we thought about there's two limiting factors of how much of an area can you do. One is the vehicle battery life. The AUVs can only run underwater for so long before they need to be brought up and charged. So you can do about a 24-hour mission. And then you had onboard storage. So the camera system, its hard drive can only hold 2 terabytes before it's full. So we kind of knew the 24-hour mission, we would fill our data storage before we reached our 24-hour mission. So each image is 12 megabytes. So if you have 2 terabytes of storage, that comes out to basically you can capture 166,666 images, and that would take about 12 hours traveling at 3 knots with a frame rate of 4 hertz. So taking 4 pictures every second, which provides you adequate overlap. And so you could then convert that time period, speed, and it basically comes out to, theoretically, we could do about 250 meter by 250 meter box, which would be equivalent to about 12 football fields in size in a 12-hour mission. And so that's, it could do 12 football fields, but honestly, with those Williamsons, you actually lose about half that. So theoretically, we could probably do about 6 football fields worth of imaging on the seafloor within 12 hours, and we'd fill up our hard drive, which is a very significant. I mean, that's a large chunk of the seafloor to get 100% imaging of. And now the camera systems have upgraded, and they actually hold 4 terabytes now. So we could do about 24 or 12 football fields, which is about 15.86 acres of the seafloor in a 24-hour single sortie, which is just a heck of a lot. So we're still working on that. We haven't been able to do that yet, but we think we've kind of figured out the way forward on that, and I think that will be extremely beneficial for documenting large dispersed sites over time. So some of the things like to sort of close out, I've got just a few more slides. Some of the issues that we want to consider with AUV-based imaging, right? It is really fantastic technology. It's allowing us to map in and document archaeological sites in deep water, which would be very difficult prior to that. As I just showed you, it's got potential to be able to do very, very large areas. But there is some things that we need to consider. One is mission times. To run these large areas, you're talking anywhere from several hours to 24 hours. And that's going to take away from your wide area survey or your other data collection. So for this project, we had 2 vehicles. So if we were to use one for imaging, that means only one is out searching for more sites. So you always have that trade-off. The size of the data collected, we're talking terabytes of data, which even just downloading terabytes over a cable from the AUV to the computer can take 12 to 14 hours just to get the data off. Then you have to back it up onto hard drives. You have to back it up onto your NAS system. All of that, just like when you start to get these levels of data, just makes everything go so much faster. Processing time to do these models. Some of these three-dimensional models, like this B-29 one, that took us about 2 weeks working pretty much nonstop for 14 days to produce that model because of the amount of images and then the sizes. And then the size of those mosaics, like I said, could be terabytes. So, there's certain laptops, you couldn't even open those up because they would just crash your laptop. And so we've been trying to work through different ways of dealing with that. And then in the field is, can you realistically process these in the field? No, it just takes too long. If you're only in the field for 12 days, you find a site halfway through, and then you try to go document it 2 days later. Well, you have 4 days left before you leave. You won't be able to process it to know, did you miss anything? Was your navigation off? And so there's always this risk of getting back and realizing that something went wrong and you didn't actually capture the data you were trying to capture. Many of these sites are remote and cost a lot of money, and you simply can't go back. And then lastly, we wanted to analyze sort of the ROV versus AUV and sort of what are the pros and cons of each one. So ship requirements. So both of them require a fairly robust ship, although the ROV probably requires a little bit more. It typically needs what's called dynamic positioning. So the ship is able to basically sit still in the water, even in moving water with currents. So it can stay right over your site because the ROV is tethered by a line going to your ship. And so that just takes a special type of ship. Not all ships have DP on them. You need deck space. So larger ROVs can come with vans that have the different viewing packages in them, basically all the topside material. Those can take up big deck space. So the AUVs are a little bit smaller, but they have their own deck space needs. You need large cranes to lift both of these things are heavy. People can't lift them in, and then you need electrical power requirements. These are very high voltage batteries and stuff like that. Availability, generally ROVs are a little bit more available. They're used very readily in a lot of academic and scientific research, as well as throughout like the whole oil and gas industry. So they're a little bit more readily available. If you don't have one at your research institute, you can go out and contract one. Although AUVs, particularly as you start to move into more advanced deepwater AUVs, are fairly rare, pretty much confined to mostly academic institutes and the U.S. military. So they're a little bit harder to come by. Cost, the AUVs tend to cost a little bit more when you're comparing an AUV like this, maybe in the $2 million range, to a working class ROV, which might be in the $5 to $10 million range. 3D versus two-dimensional. The AUVs can actually, even though they're taking two-dimensional images in a single plane, the computer algorithm actually can make three-dimensional models still, but you just don't get as rich. It can't get under, you don't get these sort of side angles as much, versus an ROV where you can do those circular patterns, you can get a lot of images, you can get low, so you're seeing under objects, and you're getting images from a whole bunch of different angles, tends to give you a much richer three-dimensional model. Real-time feedback versus processing. I noted how with the AUV, right, mostly we're going to see that data, work with that data, know if there's problems with that data after the field portion of the project is done, where the ROV, because it's tethered, we're seeing it real time. So it's very useful for instant feedback where you're looking at a site, you see something interesting, you want to go over, you want to spend more time. In theory, you could park the camera in front of that while you're trying to figure out what you're looking at for hours and hours and hours, where you can't do that with the AUV. Other tasks, there tends to be a little bit more stuff. AUVs, there's multiple sensors that you can do. You can do the general survey stuff that we do with them. Whereas an ROV, you can most of them come with manipulator arms, and you can grab things off the seafloor. And the last thing would be object relief. So the image there of that large shipwreck, That would be something very difficult to document with an AUV. We'd have to fly very high because the AUVs can't react very fast, particularly to things rapidly appearing in front of them, obstacles. So an AUV would likely just run into the side of that ship, possibly damaging your AUV, which is actually a picture up above. We ran it into a rock and we almost lost that AUV. You can see its hull coming apart. And so an ROV is much better for things with high relief that we can sort of take around. So the last thing I'll end with is what's next. So we want to continue to work on trying to ID the unidentified aircraft, the B-29 and the TBM Avenger. We still don't know the exact aircraft for any of those, so we're still working diligently on that. We're currently trying to put together a peer-reviewed article about this project and our findings. And then obviously the big question is, where are all the planes? You know, we went out there to look for 12 B-29s, and we only came up with one of them out of two surveys now, the 2016 and ours. So the question remains, where are they? It is a very difficult seafloor to operate in. And I believe that there might be out in deeper water. That blue line there, that is the 600-meter contour. So that's as far as we could go with our current vehicle. But our laboratory does now have a 3,000-meter rated vehicle. And so hopefully sometime in the future, we can get our 3,000 vehicle out there and expand our research. So with that, I want to thank everybody for coming. Looks like I saved some time. We can do some question and answer time.
Great. Thank you so much for your presentation. This is Cassandra again, everyone, and we have some time to answer your questions. And we have already had one question come in, so I will pull that up for us. The Williamson turns take up so much time and battery power. Have you explored a different turn pattern or try to be more efficient with the time and battery? I think you said camera was off for the turns, so you've already made strides.
Fantastic question, Mike. And yes, that's something that we've tried to work on both with Voyis, who's developing the system, as well as our own survey methodology. So we did some work here in La Jolla, where again we were trying to do large areas, and we tried what we call to walk the box, which would basically the vehicle would sort of drive its long line, and then rather than doing a Williamson, it would make a 90-degree turn, go up to about the middle of the survey box, 90-degree turn, and then it would kind of repeat, and each one of those sort of rectangles would advance it 1 meter and, up the survey box. It's kind of hard to maybe say out loud without an image, but so the answer is yes, we did try that, and we thought it would work better. In reality, it actually proved us that it worked worse. When we tried to walk the box, it was sort of trying to anticipate its 90-degree turn coming up, so it was cutting short in our survey area. So we, in the end, decided that the Williamsons are the best way to go. In theory, the camera should be able to be programmed to toggle on and off whenever we want it. And so we should be able to know, okay, this is the end of the survey line, it's going into the Williamson turn the camera off, do the Williamson turn, now I'm back on the line, turn the camera back on, so that we're only capturing images in our survey box. Unfortunately, there's a bug that nobody's been able to figure out, and so we're still waiting for that update. So once that update gets passed through, that should relieve that and allow us to only fill our hard drive with permanent images and not a bunch of extraneous ones to the side. But great question.
Thank you for your response. And we're still waiting for other questions to come in.
Cassandra, I can go ahead and ask a question if that's okay.
Yeah, go for it.
Awesome. Yeah, great talk, Drew. Really interesting work. I did want to return to some of the overall themes of your project in particular, and I wanted to highlight an important aspect, which was the search for and documentation of U.S. service members missing in action. I wondered if you could speak on maybe how your research and the material that you've recovered has been received by family members of potentially lost service members. And along those same lines, could you provide any advice for future research conducted in these missions and in these areas, and how to go about informing and including families of service members in research?
Yeah, also another really good question. So, when you were sort of saying my bio, I used to work there's an agency called the Defense POW MIA Accounting Agency, and they're part of the Department of Defense, and they're tasked with sort of the discovery, repatriation, and identification of U.S. soldiers that are missing in action. And they generally cover World War II, Korea, and Vietnam are the main areas. Just for those who may not know, there's still about 81,000 individuals still unaccounted for. The majority of those come from World War II. I think there's about 5,000 for the Korean War, about 1,500 or 1,600 for Vietnam conflict. So when we go out to do this type of research, whether it's, this one was a little bit broader because NOAA's purview is more large scale. They very much support DPA's mission, but that's technically DPA's mission. NOAA is much more exploratory. And so what we try to do is combine, right, where we're collecting multiple sets of data, where we're interested in the individuals that might be associated with these B-29s, and also just sort of documenting just like a general archaeological survey. What else is down there? And we would document if we found ships or anything else of significance, which is really important for the cultural heritage of that area. With this case or these cases, I don't have the exact number. I want to say there was about 72 individuals that make up the missing in action for these B-29s. When we document the sites, so the one B-29 that we worked, what we're looking for is information that would, one, be indicative of the aircraft. This is why the ID of the aircraft is very important to us, because there is one aircraft, I think, in that general cluster 4 that has no MIA associated with it, and the other 3 do. So what we want to do, particularly being such a deep water case, that would be a very difficult excavation to carry out to recover those remains, is we want to make sure that it's the correct aircraft. If we can ID the aircraft, we also try to document what components of the aircraft are visible, where are those, how are they spread out, and we're looking for any indications of particular crew positions. Again, not all aircraft have all 11 individuals missing. So if one aircraft only has, say, the pilot and co-pilot missing, and the other 9 individuals were recovered, then it's really important to try to locate the cockpit and try to prove that this is the seats or the area where the pilot and co-pilot, because that's where you want to target and focus a recovery effort in the future. So we're looking to try to discern various components, where individuals would be in the aircraft, and then any evidence, whether that's actual physical remains that might be seen on the surface, as well as evidence such as parachutes and stuff like that. That would be what we call life support. They're not definitive evidence, but they're very good circumstantial evidence suggesting that an individual might be close by. Again, that's where you would target. DPAA is the agency. Anybody who has loved ones that are missing, I think it's dpaa.gov is their website. Just Google DPAA, it'll come up. They are a great resource. They have a contact page. You could talk to them. Our organization, you can find me at Scripps, but I'm also part of Project Recover, which is a larger sort of 501c organization that's dedicated to using technology to search for and identify sites that are related with individuals that are still missing action. We share all of that data with DPAA to try to help them go out and do recoveries on sites. So those are different outlets that are out there.
Awesome. Thank you so much for your response. And then we had a question come in through the regular audience chat, so I can't display it on the screen. But Eric said, I might have missed this detail, but do you retrieve the anchored reference devices for the AUV?
Yes, we do. So we leave the anchors on the seafloor, but they have an acoustic release, so we can send an acoustic message, and they have a sort of mechanical release, and they're buoyant, so they float up to the surface. So they're fairly expensive acoustic instrumentation, so we want to make sure we can recover them after every mission.
Great, thank you. And then our next question. As computer hard drives increase in capacity and size, are there plans to upgrade storage capability on future missions beyond 4 terabytes?
Yeah. I think as we continue to get more and more data storage capabilities, we'll continue to increase those with the cameras. Again, we're already starting. I mean, hopefully, this is where AI and automation, and there's a lot of work being done in this already, can kind of help us. Where I mean, we're just getting so bogged down with processing. So I think that's the other area we need to hopefully technology continues with our processing speeds and capabilities on our computers, but also looking at ways that we can do automation using AI that maybe automate some of those steps so that they're truly running 24 hours a day rather than someone starts a part of the process that's going to take 18 hours. It stops in the middle of the night. We lost 6 hours for them to come in the next day, where some of the stuff can be increased. Yeah.
Thank you. And then this will be our last question because we are coming to the top of the hour, but it was a follow-up. Have you calculated a theoretical data capacity ceiling based on operational time limits?
So yes, it's sort of, I use a 12-hour image or a 12-hour. So 166. So we double that for 4 terabytes and 12. So look at about 30 acres, 24 football fields, 30 acres for upgraded 4 terabytes and 24-hour, which is about our maximum runtime with our battery limitations. So yeah, an incredible amount of C4.
Awesome. Thank you so much. And thank you again for joining us today and sharing your work with us. And thank you, Garrett, for organizing today's event. Garrett, do you have any final comments?
Yeah, thank you so much, Dr. Pietruszka. Very interesting work. And thank you so much, Cassandra, for facilitating. I just wanted to mention that our next NOAA Ocean Exploration Seminar, co-hosted with the library, is currently scheduled for September 3rd at 4 p.m. Dr. Amy Wright, an archaeologist with the National Park Service, will discuss her research, also in the Mariana Islands, on Guam, discussing a biogeographic and maritime cultural heritage landscape. More information will be coming out in the next few weeks about this seminar, so make sure to stay tuned until then. Thanks everyone again for joining, and have a great rest of your day.